So again, I've seen some people start, I mean, yes, like a lot of other things, we're doing algebra, so coming up with equations, and people started looking at and saying, well, when you don't know something, a certain number, we call it typically a variable, and a lot of you use x, which is totally fine. And then making sure, and I saw a couple who started out by saying x minus 9, and then just remembering when you're reading that sentence, it's a certain number is subtracted from the numerator and added to the, so from means that numerator will be 9 minus x and 18 plus x. That is a correct setup. 19 plus, yeah, sorry. 19 down here. So that's a correct setup. And then yes, guessing and checking can get there, but that's not the point and scope of this course. It's to think, how can I use my algebraic skills to solve that? So then that's where some are stuck and some are working. And but I believe the guess and check said we came up with an answer of 2, because if you subtract 2 from 9, you get 7. If you add 2 to 19, you get 21. And 7 over 21 is a third. But the question is, how do you get there algebraically? So we know the answer is 2. So this would be a good example of, if this were a problem out of your book that you're doing, all those problems you're doing, the answer in the back would say x equals 2. Your job is to find out, how did we get there? What are the steps and processes? What algorithms, fancy word for steps and processes, did we use to get there using my algebraic skills? Because while guess and check may work for simpler ones like this, they will get more complicated. So continue on, find a proper method for solving. And for those of you who follow your grades that get put in, if you're wondering, thinking tasks, it's in there in your grade book. And I give an explanation of what thinking tasks are, and you get graded every chapter on thinking tasks. These are the thinking tasks. You get graded on participation, inclusion of other people, communication with other people, making sure that you're working and processing through that. So on days when we're all at the boards, I'm looking to see, are people actually engaged with what's going on, or are they sitting back? Are they resourcing with other people, connecting, communicating, figuring out, even if it's a wrong solution, but a solution nonetheless? Back in the day, if I would have had something like if you would have had something like that, how would you have solved that? If you had y over 12 equals 1 over 100, how would you have solved that? I heard it. Cross multiply. If you did cross multiply, you'd have 100y equals 12. Okay. What's the difference between the green and the white? Not much, except we've just added a step in there. Give that a try. You're going to multiply the numerator of the left one times the denominator of the right one. So what we're actually doing, if I go back to the green one for a second, I multiplied everything by 1200. Why, you say? Because this is 12, that's 100. My common denominator is 1200. And when I do that, the 12s will reduce on the first one, leaving me 100y. Over here, the 1200 times 1 is 1200. 1200 over 100 is 12. What I'm doing over here is the same thing. So that's what cross multiplying is, but I multiplied everything by 3 times 19 plus x. And when I do that, the 19 plus x and this 19 plus x reduce, leaving me with 3 times 9 minus x. On this side, I have 1 times all of this. So I'll have 3 times 19 plus x over 3. The 3's reduce because, again, they're only multiplying, leaving just the 19 plus x. So cross-multiplying, which is a process you learned probably a long time ago, maybe even so long time ago you forgot about it. But what we're really doing is we're multiplying everything by the lowest common denominator. And when I do that, I eliminate all my fractions. And then, yes, 27 minus 3x, distributive property, equals 19 plus x. And then depends on how you want to go about doing that one next. I like having my x's positive, so I'm going to move them to the right side. Add 3x to both sides. I'll have 27 equals 19 plus 4x. 4x equals 8. 27 minus 19. X equals 2, which was our guess and check. All right, so we did that one. Now let's go back and do these, solve these super quick with your groups or at the boards if you're working at the boards. Bless you. So yeah, it could be a couple ways of solving each of these. That first one there, probably the shortest method would be to look and say, wait, they have the same denominator, which means the numerators must also be the same. So x is 3, just it comes out straight that way. Or you could say, well, I want to get rid of them. I want to get rid of my fractions. If you would have done that, you would have said, well, I'm going to multiply everything by 2. And when I do that, I mean, if I were to show all those steps in that, it would be 2x over 2 equals 6 over 2. Because 2 is the same as 2 over 1, multiplying fractions. And then I'd reduce, and I'd have x equals 3. Third method would be to do cross multiply. 2 times x is 2x. 2 times 3 is 6. Divide both sides by 2. X is 3. So either of those 3 will all be fine. Whichever you like, go for it. The next one, again, depends on how you like to think through this. I would go, well, I'd multiply this by 2 over 2. But I'm only going to multiply the left side by 1. And sometimes people get confused, like, but up here you multiplied everything by 2. That's correct, I did, because if I'm going to multiply by 2, I'm changing the size of something. I'm changing its value. If I multiply by 1, I'm not changing value because it's going to be the same number. It's just going to look different. So when I do that, I would have 2x over 6 equals 5 over 6. And then since they have the same denominator, I have those that are equal. 2x equals 5 or x equals 2.5. Divide by 2. Now, you can do cross multiply and divide. 6 times x 6x. 3 times 5, 15. Going to get you the same place. And then I heard someone else say, well, but if you look at this 3 and that 6, if I want them to be equal, I could multiply this by a half and this by a half. Is that legitimate? Can I do that? Yeah. What is a half divided by a half? Anything divided by itself is 1. So I'm not changing the value. So half of 5 is 2.5. Half of 6 is 3. It's going to also get you there. Down here, if I do it slightly different way, I could say, well, what's my lowest common denominator? 15. Yeah, common. Have to be a common denominator between 3 and 5. The smallest number that they both can divide into is 15. So if I multiply both sides by 15, I'll have 15x over 3 equals 105 over 5, if I multiply it right. 35 and 3, and that's 105, yeah. Not over 5. Yeah, over 5. And then, what happens here? 3 goes into 15, 5 times. 5 goes into 105, 21 times. All right, because 5 into 10 is 2 times. There's no leftover, so then 5 into 5 is once. But if you look at this, this is the same as if you would have cross-multiplied. 5 times x, 3 times 7. Final answer, x equals 21 over 5. For exams, leave it like that. Don't make it a decimal. It just wastes time having to pull out your calculator. Calculators are a tool, but if it's going to slow you down, it just slows you down. Try these. So with the first one, if you recognize they already have the same denominator. So if they're both divided by 7, then the numerators have to be equal. So the shortest path would be to say, well, x minus 2 equals 5. Now we also would have got there if I would have multiplied everything by 7. I'd have 7 times this parenthesis set in the numerator. I'd have 7 times 5. And then my 7s over 7s would reduce, leaving me the same thing. And then x equals 7 by adding 2 to both sides. We can use that same idea on the right and say x plus 6 equals 2 times x plus 2. Why can I say that? They have the same denominator. If the denominators are the same, then the numerators have to be the same because they're equal fractions because the equation says they're equal. Well, since these are the same, then these have to be the same. And then it's algebra this thing. X plus 6 equals 2x plus 4. Subtract x, so I can keep my x's positive on the right-hand side. I'm going to subtract 4 to move the numbers over. It's identical values left and right. To keep them equal, x equals 2. And then our instinct is to say, yes, I'm done. But when we started doing rational expressions, after we did the first thing, we said we have to look at the denominator and find out what my domain restrictions are. Remember that from a couple lessons ago? So domain restrictions. You can never have a number divided by 0. 0 in the denominator is undefined. What happens if I put 2 into this equation? I get 0 in the denominator. So my solution, the only number that would work, can't work. So while x equals 2 solves the numerator, it makes the denominator undefined, which means this entire problem has no solution. All right. Now, if you would have done cross multiplying, I'm going to kind of crank through it quick, only so we can see it. I would have done x plus 6 times x minus 2 equals 2 times x plus 2 times x minus 2. And then we're going back to our fantastic FOIL. X squared, x times x. 6 times x is 6x. X times negative 2 is negative 2x. Combined, it's plus 4x minus 12 equals 2 times x squared minus 4. X plus 2, x minus 2 multiplies to x squared minus 4. So then that would be 2x squared minus 8 equals x squared plus 4x minus 12. To solve quadratics, I need to set it equal to 0, which means I'm going to subtract an x squared from both sides. So this will be x squared. I'm going to subtract 4x from both sides, so now I'll have 4x on that side. I'm going to add the 12, that'll be plus 4, and this equals then 0. So I moved everything to the right-hand side. And now I say, is that one of my special circumstances? The answer is no, it's not. Well, is there a greatest common factor? No. Is this the difference of squares? No. Then I look at A times C. Well, the first number is 1. So it'd be 1 times 4, which is 4. And it's a positive 4, so I'm thinking of two numbers that multiply to positive 4. 1 and 4, negative 1 and negative 4, 2 and 2, negative 2 and negative 2. Do any of those numbers add to negative 4? This set does. Negative 2 times negative 2 adds to negative 4. Negative 2 times negative 2 multiplies to 4. I would have 0 equals x minus 2 and x minus 2. If two things multiply to 0, that means this has to be 0 or this has to be 0. What makes this 0? 2. That was my solution up here. What makes this 0? 2. And that was my solution here. So either way, now, was this faster? Yes. Is this still possible and doable? Yes. Do they give me the same answer? Yes. Resulting in no solution because I cannot have 0 in the denominator. Now we've worked up to this one, which will be a little bit more room and space because it's not the same denominators. So now I need to have a same denominator. So I leave this one to your struggles for a little bit of time before we come back together and do it together. what will one part of the denominator have to be? Say it again.
2x.
Almost.
2x minus
2x minus 1. This has to go together. In the denominator, this is a full thing. You got to consider this, even though it's not always drawn there that way, but it has parentheses and really represents one item. This is one item in the denominator. This has the same thing. This is something new and different, which means my common denominator will have to also include times an x. And now, you don't have to put it in the back. You can put it in the front if you want. If that makes you feel better. But that's my common denominator. So then, the many ways you could go about approaching this, I will show you one way. Or we can talk through this. I'm going to multiply everything by the common denominator, which is x times 2x minus 1. It's over 1. So then what I'm doing is I'm really thinking a giant distributive property. It's going to multiply in here to everything. And I'm going to erase this down here for now. So when I do that, I will have the original 2x times x times 2x minus 1. And it's going to be all over 2x minus 1. So that's that first fraction. Plus, I've got the 1 times, actually make this white so it's consistent. So that was the original fraction, 2x minus 1. 1 times x times 2x minus 1 all over x. And on the right-hand side, I'll have 1 times, so it's going to be x times 2x minus 1 all over 2x minus 1. Now, like I did up here with green, there are parentheses around the denominator. I do that so that sometimes it just helps me visualize what's what. So I see this entire parenthesis set. There's another parenthesis set that's identical, and this parenthesis set is being multiplied by an x and then multiplied by a 2x. So I have 4 things in the numerator. I've got a 2, an x, and the parenthesis set, all being multiplied. Denominator, parenthesis set. If it's identical, and I'm only multiplying and dividing, they reduce, leaving me with 2 times x, which is 2x squared. Next set over. In the numerator, I've got 1 times x times a parenthesis set. In the denominator, I have just the x. Since I'm only multiplying and dividing, this and this reduce. X divided by x is 1. Leaving me with plus 2x minus 1. Because 1 times anything is itself, so it'll just be itself. Equals, on the right-hand side, identical things in this, they reduce, equals x. It's a quadratic. Set it equal to 0. Move my x over. 2x squared plus x minus 1 equals 0. A times c is negative 2. That's the 2 times the negative 1. Oh, first I looked, there's no greatest common factor. Sorry, I got ahead of myself. 2, 1, negative 1. They don't have any common factors. They don't have x's. There is no GCF. So then I do a times c, negative 2. I need 2 numbers that multiply to negative 2. -1 and 2, 1 and -2. That's about it. Do any of these pairs add to +1, the middle number? Yes, they do. Factor by grouping. 2x squared minus x. That's the -1, so -1x. And then it'll be plus 2x minus 1. So again, factor by grouping, what we're really doing is I'm taking this +1x, splitting it into two things that are very strategic about which ones I choose. I can't just choose any two numbers. That if I were to simplify -x plus 2x, it still gets me back to x. But now I can look at two groups. This group, 2x squared and -x. Do they have a common factor? Yes, they do. They both can be factored out in x, leaving me with 2x minus 1. Does this second set have a common factor? No, they don't. So it's going to be plus 2x minus 1. Do those two sets that are being added have a common factor? Yes, they do. They both have a 2x minus 1. So I'm going to factor that out in front. And when I do, I factor this out in front, I'm left with an x. When I factor this out in front, I'm left with plus 1. Because really this is 1 times a parentheses set. We normally don't write 1 times, but this is one of those times when it actually helps us to remember that, oh, that's 1 times that parentheses. So when I factor that 2x minus 1 out, all right, and this equals 0, equals 0, equals 0. If I have two things that multiply to give me 0, one of them must be 0. So either x plus 1 equals 0 or 2x minus 1 equals 0. If x plus 1 equals 0, subtract 1, x equals -1. If 2x minus 1 equals 0, that's 2x equals 1, and then divide by 2, x equals 1/2. So I've got two numbers that are solutions, but then I need to go back to my original equation and say, what happens if x is -1? -1, -1, -1. So none of the denominators are 0, which is a good thing. So this is a solution. What about 1/2? 2 times 1/2 is 1. 1 minus 1 is 0. So while this is a solution to the numerator, x equals 1/2, if I go back to the original equation, it makes my denominator 0. So while these two are both algebraically answers, this one is a solution. This one is not a solution. So yes, we can do all of this work, and this was a lot of work, and get answers and go, yes, I got answers, and still one of the answers doesn't work in the original equation. In a scenario like this, I'll go ahead and help us set it up. A plane flies 465 miles with the wind and 345 miles against the wind in the same length of time. So whatever the time is, it's the same length of time. We're also talking distance. Jogging our memories back to formulas and equations, distance equals rate times time. All right. You've driven cars, you've ridden in planes, mostly driven in cars. Rate times time, 80 miles an hour for an hour, you're going to go 80 miles. Of course, you're never going to go 80 miles an hour in the state of California because that's illegal. Right? Nod, sure, yeah, right. Okay? So what do we have going on here? It says a plane flies 465 miles with the wind and 347 miles against the wind in the same length of time. What do we not know? Well, we do not know the speed of the planes. All right. If the speed of the wind is 20 miles an hour, find the speed of the plane in still air. So we're going to assume that the plane in still air is going to have a constant speed. So the rate and the distance, 465 miles, equals rate. Which one is this? With the wind? Yes. Rate plus 20. So with the wind at your back, you're going to go faster. So with the wind, you're going to have a faster rate. Times time. I have a second equation. 345 miles. That will equal the speed's plane minus 20 because you're going into the wind. Times time. And yes, this is actually how it works. Like if you could actually physically run 20 miles an hour, but only 20 miles an hour, exactly 20 miles an hour, and there was a 20 mile an hour headwind, you would actually go nowhere. Because you would be matching the exact speed in which the force is coming at you. So now I have two equations, two variables. I can start thinking about how in the world am I going to solve these equations. Any ideas? This would be the group participation portion of our morning. You could use elimination, but right now we've got variables times variables and things going on. In a scenario like that, I usually look at saying, can I solve both equations for the same variable? If I can, then I can set them equal to each other. So if I look at this first equation and find out what this one here, I'm going to solve it for t. So if I look on the right-hand side, and I'll just go ahead and rewrite it down here below, because we don't need that other information right now. 465 equals r plus 20 times t. If I want to solve for t, that means I want to get rid of everything that's not a t on the right-hand side. I will divide by r plus 20. I will then have t equals 465 over r plus 20. I can do the same thing with my other equation. If I divide both sides here by r minus 20, I'll have my second equation, which will be t equals 345 over r minus 20. And this is where then I would go to substitution. What does t equal? T equals this. T also equals this. And if it's the same time, because it says it can travel these distances in the same time, that means the times are equal. So my equation would be 345 over r minus 20 equals 465 times r plus 20. Now, I would go back to where we started and I'd cross multiply. $345 times r plus 20 equals 465. Oh, that's way out of line. Sorry about that. 465 times R minus 20. And at that point, you should be able to finish that out. Distributive property. Move all the variables to one side, numbers to the other. It's getting you back, hopefully, into some familiar ground. This one, which is way out of sync now. There you go. Getting in the habit of saying, okay, how do I get going? Where do I start? What kind of equation do I set up to get us working in that direction? I moved on to the next one. Yep. Usually when I say you can probably finish that one on your own would mean you'll finish that one on your own. All right. And if you finished it already because you're working hard, you probably already got an answer. But now we go to the next one. Similar kind of ideas. So one hose can fill a tank in 45 minutes and two hoses can fill the same tank in 20 minutes. How long does it take the second hose alone to fill the tank? Do we know anything about the rate at which each hose operates? Does it say they operate with the same amount of water coming in? Or is it different? Or does it not say? It does not say. All right. But think about it the same way. It's not distance equals rate times time. Here we're going to have volume equals rate times time. Yes, sir. So with that, they have the same volume because it says it's the same tank. So we're going to think about it like, all right, well, tank 1 and tank 2, I guess. Tank 1, or it's not even the same tank. So tank 1 time, it's going to be 1 hose. So the volume equals just the 1 rate times time. So this is 1 hose. With 2 hoses, it's going to volume, why don't I put parentheses, equals rate 1 plus rate 2 times time. Just bear with me for a second. So I've got 2 hoses. They have, as far as I can tell, different rates. But we know that the first tank with the 1 hose took how long? So rate times 45. And the rate is the rate that the first hose can operate. All right. The second time, it was the 2 hoses. And it took how long? 20 minutes. All right. And this R over here is technically my R1. Now, if you don't like using subnotation, and you're like, I prefer just to have 2 separate variables, you could go back in here and say, okay, well, let's just go ahead and make this something I'm a little more comfortable with. And instead of R1, I'll call it X. And the other one, instead of R1 and R2, I can call it X plus Y. All right, and then what do I know? Well, they have the same volume, so I've got 45x equals x plus y over n times 20. So what we're going to actually end up with is an equation, not a solution in this scenario. Now, we would have needed more information, and you didn't know that at the beginning, but we would have needed more information if we wanted to actually say, well, how do the tank, like, what do we know about the ratios and the comparisons of the 2 hoses? All right. But getting you an idea of here how to set this up, because you may see a problem similar to this on the check your understanding problems from the book. All right. But between that one and looking back, whiteboard there. For some reason, that one's all there. Okay, so we are nearing the end of chapter 6. We have one more day of chapter 6, which is our next day that we're together. If you've been following along online, on the Check Your Understanding pages for each module, there lists all the problems that are out of your book that I'm expecting that you are doing on your own. All right. Some people come into my classes when they get to college and they go, wait, you're not going to collect homework? And the answer is no, I don't. That is for you to know that you know what's going on. I almost always give you problems where the answers are in the back of the book. So you can do the problem and look to see that I get the answer right. Like we started out today when we said, oh, X is 2. And then you go back and say, how did I figure that out? What processes did I use? And if you don't know, then referencing back to some of the notes you're taking in class, you're going back and looking at, and our textbook has actually some really good example problems in each chapter. You're looking at those examples, looking at how they did it, because they in there articulate a lot of the steps and why they went from here to here to here. If that still is struggling, then I would go and say, read your textbook. Math books aren't typically, great page turners where people are like, wow, this is fascinating. I mean, unless you're a math geek like me, then of course they are. And yes, I do read books like that for fun. And yes, it's weird. But going back and looking at those example problems, if you're still, so again, you're looking at what we did in class, some of the thinking task questions that we worked on, notes that you're writing to yourself when I say, hey, now's a good time to write some things down, is you process what happens every day in class. I don't know what you do, but I would recommend that after class, you spend some time in what I call synthesize. Synthesize. I think I spelled that wrong. Synthesize is take the information, think about it, and try to make a summary of it. All right, because this would be doing it on your own of what we've talked about, some examples we did, like, yeah, professor kept saying, make sure you don't do this, make sure you don't do this. Maybe that's a good thing to write down because he's repeated it like 5 times about being careful, especially when reducing. Looking at things like difference of squares and knowing how to factor that. Like he said that again today, another time, probably pushing 40 times he said it so far. In class, synthesize information, work on your Check Your Understanding problems. If they're not making sense, you're going back and looking at the examples to see if you can make sense of that there. If that still is not working, read some. They might have some words in there, and if you're a different learner, you might read it. And if it helps, read it out loud. Yeah, it seems weird, but maybe do it alone. But if you read it out loud, you're going to hear it, and sometimes when you hear your own words, like when you write your own papers, if you read it out loud to yourself, you'll oftentimes catch a lot of your mistakes because you'll read it and say, oh, that didn't sound right. Because I speak English much better than I type English. But if you do that, you're going to then read it and say, oh, that might make some more sense. And if after all of this and you've done all of these and you're still not getting them, maybe you have a study partner in this class or a roommate who's taken this class before and they aren't being able to help you, yes, then you're emailing me and we're setting up a time to meet. If you try to catch me and say, hey, can I meet at such and such time? There's a chance I might not be able to, but if you email me and say, hey, here's a time or here's this, I'm like, usually the answer is yes. And whatever the room is next to the coffee shop, is that just the Union or whatever they call it bigger? I'll usually be hanging out in there during that time. I'll have a table, we'll sit down. You pull out your problems that you've been working on, you show me your work, and we say, let me see if I can help you find where you're making your mistakes. That's going to be the most efficient use of your time and my time. And as we prepare for the next exam coming up the week after spring break, it's not, I don't think it's the Tuesday. I think it's the Thursday after spring break. I'd have to look at the calendar again. But if you go on to the syllabus page on our Canvas, go to course summary, it will list in there all of the dates, including the exams and the final exam for what we're doing in here. Much of the online discussions, there's not as many between now and the end. I put those there at the beginning to get us kind of going and get the mathematical juices flowing. But pay attention to that page for when due dates are so that you're not missing those things. We've had several. And if you're realizing I haven't hardly done any, then maybe you missed some. And then we've got the thinking tasks. So we're approaching that halfway through the semester moment, because we're in week 7 now and there's 15 weeks. That it's kind of the grind and the push to the end. We're going to start picking up the pace in the other chapters. If you've thought we've been moving fast already, be ready, because we're going to pick it up.